Coronavirus disease 2019, or people normally call it Covid-19, is a type of disease caused by SARS-CoV-2 virus, and it was first identified in the end of 2019. The emergence of Covid-19 has brought a huge impact not only to the economy but also the freedom of human life. Hello and hi everyone, my name is Elila, and in this video we are going to study the transmission of Covid-19 by the use of mathematical models. Covid-19 has led to a dramatic change in human life. Many businesses were forced to close down and led to the disruption in most of the factory sectors. Because of these conditions, millions of people are in the risk of falling into extreme poverty. Hence, it is really important for us to control this outbreak.
There are four main objectives of this project. The first one, to introduce a mathematical model to study the outbreak of COVID-19. Second, to compute the basic reproduction number of this mathematical model. Third, to analyze the local stability of the model. And the last one, to perform numerical simulations to depict the dynamics of the model. Before I started to do this project, I have reviewed three main articles for my reference. The first one, written by Samuel et al., a mathematical model for COVID-19 transmission dynamics with a case study in India. Second one, COVID-19 pandemic in India, a mathematical model study written by Biswas et al. After that, mathematical modeling, analysis, and numerical simulations of the COVID-19 transmission with mitigation of control strategy used in Cameroon by Giles et al.
Before we start to do the project, the first thing we have to do is we divide the total human population into four main categories: susceptible as asymptomatic A, reported symptomatic infected I, and unreported symptomatic infected U. The mathematical model we use is this, and from the flowchart given, we could see that S population will increase by lambda factor and decrease by mu, while A population will increase by these factors and decrease by mu and gamma. U population will increase by gamma and decrease by mu, eta U, and Q gamma factor. I population will increase by Q gamma and decrease by mu and eta I. This is the description and explanation of each parameter used inside the mathematical model. After that, we find the equilibrium points such that disease-free equilibrium and also endemic equilibrium of the model, then followed by basic reproduction number, R0. After that, with some computational processes, we come up with two theorems. Theorem 1, disease-free equilibrium is locally asymptotically stable if R0 less than 1. Theorem 2, endemic equilibrium is locally asymptotically stable if R0 greater than 1 and fulfill these conditions. To verify our theoretical results, we perform numerical simulations by using MATLAB software. The parameter we use is this, and we take this as our initial values. We obtain 0.4006 as our R0, which is less than 1. From the graph obtained, we could see that S population converges to lambda over mu, which is approximately equal to 10,000 individuals, while population of A, I, and U are each converge to 0. This shows that our model tends to converge to DFE whenever R0 is less than 1. From here, we could see that no matter what is our initial values, the graph still converges to one point, which is E0. Next, we are still using the same initial values and parameter values, except for beta, we change it into 0.35. R0 computed is 2.8041, which is greater than 1. Here we could see that S population converges to S star, which is approximately 3,500 individuals. Population of A converges to S star, which is approximately equal to 40 individuals, while I converges to I star, which is approximately equal to 4,200 individuals, and U converges to U star, which is approximately equal to 900 individuals. This means our model converges to EE whenever R0 is greater than 1. These results are also proved by the graph obtained when we take arbitrary numbers as our initial values. The graph insists to one convergence regardless of the arbitrary initial values. As a conclusion, we first introduce a set of mathematical models and we compute the basic reproduction number of the proposed model. After that, we will analyze the local stability, and we found that DFE is locally asymptotically stable if R0 less than 1, while EE achieves local asymptotic stability whenever R0 is greater than 1. To verify these theoretical results, we performed some numerical simulations, and we found that our both theoretical and numerical results are well matched. After we're done with this project, there are three recommendations to be given. The first one, the government and policymakers should take any relevant strategies to control this disease. And the public should obey any rules, any policies that made by the government and policymakers. And the last one, for the future research, we recommend the researchers to investigate the transmission in a specific community to get a more accurate results, and also examine the effectiveness of prevention strategies in combating this disease. Here is a part of the reference list that I refer to in the completion of this project. Thank you so much for spending your time on watching this video. Bye-bye.